8.2 is on page 426, talks about power series and analytic functions. Analytic function we're not going to use much until 8.3 really, but if we take the limit as n approaches infinity of the following summation, basically you're going to take the series to infinity. And we're going to see if that could be defined as y of x. A power series about x sub 0 is looking like this. It looks like a polynomial sort of streak when you expand it. Radius of convergence, that's nothing, not a big secret. We know what that is. If we take magnitude of x minus x naught to be less than rho, then figure out what rho is. If the series converge for all values of x, we say this rho, which is the radius of convergence, is infinity. So domain is pretty much everything. And when the series converge only at x sub 0, so only at one point, we say, well, the radius is 0. And not a big secret, I told you last lecture video, we're going to do the ratio test. And we take the ratio test of the coefficients always to figure out what this L is. And this L will depend on if L is less than 1, bigger than 1, equal to 1. We go with the ratio test recommendations. This is on page 433. So I want to start with first review really quick of how that works. This is second semester calculus. This is what the entire section is in. Determine the convergence set for this power series. So that way you would start, you would take the limit as n approaches infinity of 3 to the n plus 1 divided by n plus 1 factorial divided by 3 to the n over n factorial. I'm going to write every step for the first problem only. After that, this is n plus 1 times n factorial. Instead of dividing, you multiply by the reciprocal. And those cancel, those cancel out, and those cancel out. And I'm left with the limit as n approaches infinity of 3 over n plus 1, that is 0, which is always less than 1. So therefore we say r equal infinity, and the interval of convergence is negative infinity to positive infinity. So this converges everywhere because the limit is always going to be 0. We know that exponentials and factorials dominate over anything. So if I look at the second problem, problem number 4, the same deal. We take the limit as n approaches infinity, and that's going to be 4 over n plus, let me see, that is really n into n plus 2. So that is n plus 1, n plus 3, and when we divide, we're going to multiply by the reciprocal. The 4's cancel out. This is the limit as n approaches infinity. And if I divide by the highest power term of the denominator, which is n squared, that would really be 1 plus 1 over n. That would be 1 plus 3 over n. The top will be n over n, n over n, 2 over n. That's a 0, that's a 0, that's a 0. So I'm left with 1 over 1 times 1, which is 1. So in this case, I get a 1. Now, so we have absolute value of x minus 3 being less than 1. That indicates that x minus 3 is between 1 and negative 1. So x is between 4 and 2. Well, we need to test the endpoints if you recall, because that's when it equals to 1, it's inconclusive. So let x equal 2. We're looking at the series n equal 1 to infinity of 4 over n into n plus 2. And if I put a 2 in there, 2 minus 3 is negative 1 to the n. So we know this is positive. It is decreasing, and the limit as n approaches infinity of 4 over n into n plus 2 equals 0. therefore it converged by alternating series test. So this is accepted. Up till now 2 is included. I'm trying to figure out if 4 is included. Let x equal 4. Well, I'm looking at the series n equal 1 to infinity, the 4 over n into n plus 2. And if I put a 4 in there, 4 minus 3 is 1 to the n, which is just 1. And if I compare that, that's definitely less than 4 over n squared. This is p equal 2 bigger than 1, therefore it converge. Therefore, the original series converged by the comparison test. So x equal 4 is accepted. There is my interval of convergence. And that's how we're going to do those. We're going to use what we learned in second semester calculus. You need to do the justifications just like I'm doing them. If I look at this problem, I take the limit as n approaches infinity, n plus 1, so that's n plus 3 factorial, which is n plus 3 times n plus 2, divided by n plus 1 factorial times n factorial. The x, again, we leave that alone. We just bring it in at the end when it's needed. Instead of dividing, you multiply by the reciprocal. This is going to equal the limit as n approaches infinity. If you divide by the highest power term of the denominator, you could do L'Hopital if you wish, whatever you like, but you have to show me how you're getting your answer. We get a 1. Well, again, 1, it's really going to be, you know, for us from second semester calculus or 5b, that's going to leave me with x plus 2 in there, an absolute value being less than 1, which means x plus 2 is between negative 1 and 1. So x is between negative 1 and negative 3. Again, I need to check on those, see if negative 3 is included and negative 1 is included, so I need to do the testing. I will let x equal negative 3, that will be the series, n equals 0 to infinity, and negative n plus 2, n plus 1 times n factorial over n factorial. This cancels out every time, so this one is going to be left over, but if I put a negative 3 in there, I'm going to get negative 1 to the n. But the limit as n approaches infinity of this is infinity, therefore it diverges, so that's not included. And if I let x equal negative 1, the same thing is going to happen. I'm looking at the series n equal 1 to infinity, or 0 to infinity, of n plus 2 times n plus 1. If you put negative 1 in there, it will be 1, but again, the limit as n approaches infinity of this will equal infinity, which is not 0. Therefore, this diverges by alternating by the test for divergence. Here you could do the same. You could say this limit does not exist, or you could say by no, it's not decreasing. What do you call it? Test for divergence. So here the interval is negative 1 to negative 3, not including either of those. Now, when I say here infinity, you could say does not exist because this is going to alternate between positive and negative infinity, but we assume it's the same thing. The deal was if the limit doesn't equal 0, it diverges. How about this one? Determine the convergence set for this. If I take the limit as n approaches infinity of, if you put a k plus 1 in there, that's 2 to the 2 into k plus 1, so be careful with that. Right? Divided by, here it's going to be slightly different because here we have x raised to the 2 into k plus 1 divided by 2 to the 2k, x to the 2k, and here if you reduce it a bit, you'll notice this is the limit as n approaches approaches infinity of 2 to the 2k times 2 squared, because you distribute that in. That's the part you want to be careful with here. That's x to the 2k times x squared, not x. The bottom is 2 to the 2k, x to the 2k. These cancel out, these cancel out. You're left with absolute value of 4x squared, and you want that to be less than 1, which indicates that you want absolute value of x squared to be less 1/4. And if you square root both sides, you're looking at absolute value of x being less than 1/2. In our case, yeah, I could have did that. I could have said that's 2 squared so this is geometric, right? If the absolute value of r is less than 1, so no need to test the endpoints because they're not going to work. If you let x equal, so let's do that actually, might as well. So you want to know 1/2 and 1/2. Let's see how that works. If you let x equal -1/2, you're looking at the series. Again, no need to test those if you recognize this geometric, because if r equal 1, it could diverge. But if you didn't recognize that, let's say you say k equals 0 to infinity, 2 to the 2k, -1/2 to the 2k, series k equals 0 to infinity of -1 to the 2k. The limit as n approaches infinity of -1 to the 2k, or 2. I'm so stuck on n. Does not exist. Oscillation. Therefore, diverge. And if you let x equal 1/2, the same thing's going to happen. Look at the series k equals 0 to infinity of 1 raised to the 2k. Well, that's still the limit as k approaches infinity of +1 to the 2k equal 1, which doesn't equal 0. Therefore, diverge by test for divergence. So here it's just the interval. But if you recognize it's geometric, it's much faster. And the same deal here. If I want to know the sign of x over x, well, I'll take the limit as n approaches infinity, and here they worked it out for me. That's pretty good. -1 to the n plus 1, x to the 2n x squared, divided by, if you put an n plus 1 in there, that's 2n plus 3 factorial, divided, that means you multiply by the reciprocal, now the -1 in there is useless really, because absolute value is going to absorb that. So this is -1 x squared over 2n plus 3 times 2n plus 2. This limit is 0, which is less than 1, therefore converge for all values of x. This is always convergent. And the interval will be any number, because factorial is going to dominate over that. Now here we're going to get into a very important aspect. We need this for the next sections. Can you combine those? This is crucial, something we're going to have to do as we play with those. So the idea is to be able to add two summations, and we have to do that. I'm going to start with where you should begin. If I'm adding those, two things must be true for you to be able to add them. The powers must be equal. That's where you start. So it doesn't matter which one you push up, which one you push down. This is n minus 1. Let me see the partial expansion. Okay. So if I wanted to match, I want to boost this one up. That means you're going to boost this one up, and this one down to compensate. So that's going to be the series n equal 2 to infinity. and here 2 to the n plus 1, n plus 1, times x minus 1 to the n minus 1. That's where you begin. That's always the start. If the variables don't match, there's no way of combining those, and we want to combine those. The next up, so this is done. Those match. Now we need those to match. I notice, since I can't change the power, well, if I drop one piece out of that term, so can't I say this is the series n equal 2 to infinity of 2 to the n plus 1 over n plus 1 times x minus 1 to the n minus 1. If I let n equal 1, isn't that 1 over 2 times x minus 1? If you put a 1 in there, that's the 0 plus the series n equal 2 to infinity. So that's a small price to pay because I don't want to alter the powers, then those don't match. Now I notice that those match, and it has to be the variable first, and those match. So now I could say, well, hey, that's the series n equal 2 to infinity. I'm going to have a bunch of quantities in there, x minus 1 to the n minus 1. Perfect. I was able to combine them. Of course, I could make that x to the n if I want, but that's not the goal. The goal is to combine those somehow. Well, what's going to go in there? This piece plus this piece. And don't forget, that piece. And I was able to combine them. Now, of course, if you could simplify that, you should. For this purpose of these here, we don't. We're going to do that in the next section, so maybe you should practice those. What if I wanted to multiply those two? Well, to multiply them, you really want to write them in expanded form. So if you look carefully, k equals 0, that's going to give me a positive x, k equal 1, negative 1 over 3 factorial x cubed plus n equal 2 positive x2 for x to the 5 over 5 factorial. And the list goes on. And this is cosine. If you let k equal 0, you're going to get 1. Let k equal 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and the list goes on. And to figure out what this equals, well, I need to multiply few of those. So let's see how this works. I'm going to take the 1. I'm going to multiply it times a few of those. That is x minus x cubed over 2 factorial, which is 2, plus x to the 5th over 4 factorial. Of course, there's a lot more, but now I'm going to take this and multiply it by those 3, minus 1 over 3 factorial x cubed minus 1 over 3 factorial 2 factorial x to the 5th. And I think that's all I need. I could write one more, minus 1 over 3 factorial 4 factorial x to the 7, but it doesn't look like we're going to need that. And I'm going to go for the third multiplied by those. Again, I just need to go up to x to the 5th. So if I multiply that, that's x to the 5th over 5 factorial. Now, if terms cancel out, I might have to come back and do more, but for now, it seems there's an x. It seems there's a minus the x cubed. Let's see what's in the x cubed. X cubed, there's negative 1 over 2 factorial, that's negative 1/2. And x cubed, negative 1 over 3 factorial is 6. X to the 5th, there are 3 of them. Negative 1 over 4 factorial is 24. Minus, this is 6 times 2, that's 12. this is 1 over 120. So the first three non-zero terms will be, that is 4 over 6. 4 over 6 is 2/3. Hopefully I didn't make a mistake, but you get the idea. Minus all over 120. That turns out to be 120 times 5, -5, -10, plus 1. So that, oh, that should be a plus, I think. I think that's a plus, if I'm not mistaken. Yeah, negative times a negative is a positive. I have the answer next to me. I worked this out. So that's positive 5 minus 10 plus 1, 6. That's a 4, which is really 1 over 30. But those are the first three terms. Of course, there's a lot more, but that's all they wanted. And we use those a lot in coding and stuff. Okay, I want this. This is going to need on the long run. If I take 1 plus x squared plus x cubed, this is an infinite sum and it's geometric. You're multiplying by x every time. So this is the very first term divided by 1 minus r, provided the absolute value of r is less than 1. This is the very first term divided by 1 minus r is what I'm multiplying with every time. And absolute value r is x in this case, and that's where this comes from, and that's where this comes from. Now, nothing different, we already know this. When you take a derivative, you should really list out few terms. So, if we're talking about a sub 0 plus a sub 1x plus a sub 2x squared, then okay, no big deal. When you take a derivative, you lose a term, so you boost this one up from 0. But some of those don't. X squared, for example, if it was x to the 2n, then when you take a derivative, you will have those terms listed. I'll show what that means. Well, taking a derivative is fairly simple. Just bring the power down, subtract 1 from the power on the variable, and if you integrate, ignore that's a constant, add 1 to the power and divide by that. I mean, that's constant. Well, let's see how this works really quick. Now, analytic I need in the next section really. A function is said to be analytic at x sub 0 if an open interval about x sub 0 or containing x sub 0 of this function is the sum of the powers that has positive radius, which means they converge. I do reiterate that in the next section, slightly different, but it's the same idea. It says find a power series representation for the derivative. So what you do, you list few of those, just few. Let maybe the first 2 or 3. Let k equals 0. So that's positive 1 over 1 factorial x to the 1. As you put 0 there. 1, you get negative x cubed over 3 factorial plus, and again, I just need one derivative. If I took a derivative of this, wouldn't this be 1 minus 3x squared over 3 factorial, and the list goes on? Do you see I didn't lose a term? So this does not get indexed up by 1, it stays as is in this case. And the calculus is really simple for those. Since the only variable is x, bring the power down, subtract 1 from the power. And this cleans up a bit, so might as well. Because this is 2k plus 1 times 2k factorial, those cancel out. So you're looking at negative 1 to the k over 2k factorial x to the 2k. There is my answer. That's all you have to do. And if I look at this problem, again, is 20 the same idea? 18 and 20. Okay, well, here are the same deal. If I look at this, we say, okay, well, if I let n equal 1, isn't that 1 a sub 1 x to the 0 plus 2 a sub 2 x to the 1? If I take a derivative of this, doesn't that become a 0? And this becomes 2a sub 2. So you lose a term. That's when you boost this 1 up. And the calculus is simple. Bring the power down, subtract 1 from the power. And integrating is also simple. If you could write it as a power series, there it is. So we're going to find the integral. The integral of this from 0 to x of sine of x over x dx. Well, that's very hard to do. We use this instead. We say that is c plus negative 1 to the k over 2k plus 1 is a constant. Add 1 to the power and divide by that. There it is. Evaluate it from 0 to x, of course. I forgot about that. That's c plus. If you put the x in, well, you're going to get this. But if you put the 0 in, it's going to 0 out. So there it is. It should have been f of t dt. My mistake. You know what? I'm not reading this properly. If you plug x in, you're going to get it in terms of x. So there it is. And that's my final answer. All right. Now, something that I have to do as well, I have to really alter those. We want this to be x to the k. It could be fixed if it's only shifted. If it's only shifted, shift this 2 down. Shift this 2 down. Shift this 2 down. Shift this 2 down. And to compensate, shift this 2 up. When you're done, if you let n equal 2, you get 2 times 1 a sub 2 x to the 4th. If you let k equal 4, you should get the same thing. That's a 2, that's a 1. 4 minus 2 is 2, and a 4 in there, it matches. Always check. They have to be exactly the same, but we do need to alter them. We do need to change the starting and the terminating point. And the same deal here, if it is off by a constant, I could fix it, meaning I could shift this down by 3, shift this down by 3, shift this down by 3, and shift this up by 3. And you could check if you want. Make sure that they end at infinity, so they're going to match in the long run. Just the starting and the beginning should be the same. And if you recall how Taylor polynomial works, Taylor polynomial, we say this is about x equal 1. So we say this is f of 1 plus f prime of 1 times x minus 1 to the 1 over 1 factorial plus f double prime of 1 times x minus 1 squared over 2 factorial plus f triple prime of 1 times x minus 1 cubed over 3 factorial. So that's how that goes. The idea is that to figure out a pattern, to do that, we need to figure out what those are. So f equals x to the negative 1 at x equal 1, we get a 1. F prime is negative x to the negative 2, that's negative 1. F double prime is positive 1 times 2x to the negative 3. At 1, that is 1 times 2. f triple prime is negative 1 times 2 times 3x to the negative 4, negative 1 times 2 times 3. So this is f of 1, which is 1 plus minus 1 times x minus 1 to the 1 over 1 factorial plus 1 times 2 times x minus 1 squared over 2 factorial minus 1 times 2 times 3 and that is 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed. You know what I'm thinking? And there's the list. So this is actually the series n equal 1 to infinity, negative 1 to the n times x minus 1 to the n. That's really what it comes out to be. You could check that. Anytime it's alternating, this takes care of it. If you're off, if this is positive and this is negative, then you just make that a power of n plus 1 or n minus 1, and that does the trick. Almost done. Here's another one, f equal x to the 1/2. So this is going to be f of 1 plus f prime of 1 x minus 1 to the 1 over 1 factorial centered at 1, f double prime of 1 x minus 1 squared over 2 factorial, triple prime of 1 x minus 1 cubed over 3 factorial. This goes on. Now f is radical x, which is x to the 1/2. Evaluate at x equal 1, that's a 1. F prime is 1/2 x to the negative 1/2, that's 1/2. F double prime is negative 1 over 2 squared x to the negative 3/2, that is negative 1 over 2 squared. The third derivative is positive 3 over 2 cubed x to the negative 5/2, that's 3 over 2 cubed. Maybe one more just to be sure. That is negative 3 over 3 times 5 over 2 to the 4th, evaluated at, that's negative 3 times 5 over 2 factorial. Okay, and the next one will be 3 times 5 times 7. So this is a 1 plus 1/2 x minus 1 to the 1 over 1 factorial minus 1 over 2 squared times x minus 1 squared over 2 factorial plus 3 over 2 to the 3rd times x minus 1 cubed over 3 factorial plus 3 times 5 x minus 1 to the 4th over 4 factorial times 2 to the 4th, and the list goes on. So it seems we're looking at the series n equal to infinity. There's an x minus 1 to the n on each of those. These are moving up. It seems the denominator always has that factorial. It's alternating. Now if I let n equal 2, this is positive, n equal 2, the squared is negative, so plus 1 or minus 1 will do the trick. The only problem, there is a quantity down there that I need to take care of. And that seems to be 3 times 5 times 1. Well, let's see. This is arithmetic. 1, 3, 5, a sub n is the very first term plus n minus 1 times the common difference. A sub n and the common difference is 2. That's 2n minus 2 minus 1. If I put 2n minus 1 here, let's see if that works. If I let n equal 2, I'm looking at a negative 2 factorial x minus 1 squared, and if I put a 2 right there, 2 times 2 is 4 minus 1 is 3. So that square term, it seems, oops, the square term, sorry, right there. Oh, I forgot. There is 2 to the first, 2 squared, 2 cubed, so there's 2 to the n. I forgot about that as well. Okay, 2 squared, I see it right there. Now, if I put a 2 right there, we should have a 3, but I notice this has a 1. And I notice that's the term after. So what you do, you replace n by n plus 1 to shift that 1 up. So that will be 2 into n plus 1 minus 1. So that's 2n plus 1. And that will do the trick. Now if I let n equal 0, putting a 0 there, I get a 1 over 2, 0 factorial. That is the one. So I could start at 0. Sometimes you can't. So you just drop a term and do the rest. We did that with binomial. And that's pretty much it for this section.